Hello, welcome to this online tutorial. As promised, I would like to offer you a recorded version of this tutorial. Again, we apologize for the confusion. There was supposed to be a protest tomorrow. I'm recording this on Wednesday, but it was cancelled. But now on short notice, we decided not to do the tutorials because teachers, as well as you, I assume, already have different plans. But I believe together with the screen recording, with the provided solutions, you will be able to work through this yourself. And of course, as already mentioned, you are able to ask questions about these tutorials to your teachers next Tuesday. But for now, I would like to just go through this tutorial line by line, explain what's happening, and tell you a little bit about what we're trying to achieve here. So this tutorial is about word embeddings. If you remember from the lecture, it's about a better representation of text than the document term matrix. So we are going to engage with word embeddings, very generally speaking, but we're also going to fit a neural network with word embeddings. So in a way, this tutorial combines what we've learned in the past tutorial on supervised machine learning with neural networks with this concept of a better text representation called word embeddings. We start slowly. We're going to load our packages. Again, it's going to be the tidyverse and tidytext. Later, when we fit the neural network, we're also going to load the tidymodels packages. And we're going to load a data set. This data set for this tutorial is, again, on Canvas. So you need to download it, put it into your folder of choice. And in this case, it is a data set that contains 5,002 tweets already a while back that contained the hashtag New Year's resolutions. So it's timely in the sense that soon we're having New Year's Eve. Maybe you will make your New Year's resolution. Some people like to share it on Twitter, now X. And let's see what type of text analysis we can do with this text. So I already put the data set into my folder, so I can just go about and load it here. Or I actually cannot. Maybe I'll need to set it to the source file location. And let's see. Now I can actually load it. By running ahead, wrapping around the tweets, we can always check out how this data set looks like. I'm going to make this a little bit bigger so that we can actually see it. So we see that this data set contains a lot of different things. We have, for example, already a labeled resolution topic. We have a gender and a name by the original poster. There's also a more general resolution category, whether it was retweeted or not. The actual text, now really, really badly abbreviated here, and then also when it was created and so on. So let's do some standard text analysis with this text. First, what I did here in this code, I'm creating an ID variable. Just to be sure, it's always a good idea to actually have an ID variable in your data set. We already have tweet ID here, but I'm creating a new one here. And then I'm selecting everything that I think is important to keep. In this case, it's just going to be the name, which is the poster itself, the text, which is here, this column containing the text, and as a topic, the resolution category. This is what we try to predict, right? We'll later on try to predict in which category the tweet fits. And then I'm directly gonna use the function unNestToken that by now you should be very familiar with in order to create the tidy representation of tokens. Okay, I'm gonna do this and I'll check out, and you'll see, for example, that the first tweet by Dana Marina is probably about health and fitness, and the first word actually was New Year's resolution, which is likely the hashtag itself. And she says, read more books, no scrolling. Potentially the tweet is actually continuing, of course. But with this representation, we can visualize word frequencies. How about first descriptive analysis of the frequencies per topic? And as you know, for visualizations, it's often fruitful to remove some words because filler words occur quite often. And if we would leave them in, they would kind of pollute our word cloud or our bar plot or whatever we want to plot here. And tweets actually contain a lot of things that are actually not very useful to keep, right? So the first thing that's not useful is actually the hashtag itself, New Year's resolution. We sampled tweets with this hashtag, so it's literally going to be in every single tweet. If you wouldn't remove it, the most common word that we would see in a word cloud is New Year's resolution. The same is true for resolution, right? So sometimes people name the term itself. And then there's a lot of different things that are sort of idiosyncratic to Twitter, right? So for example, RT stands for retweet. HTTP is usually the beginning of a link. T.co is then the link itself, including a shortcut for Twitter in this case. Then the year itself is also not very useful to try to get at the topic, right? This was 2014, 2015. So if they name the year, that's not really interesting to us. And also, apparently there was some common numbers used here that are also not very useful. So I'm creating my own little stop word vector here, which I will then use here to anti-join. So when I use my tidy tweets and I anti-join these words, they will be removed from it. So actually, I'll do two things. It's not just, sorry for that, but I'll anti-join general stop words, right? All types of stop words that we generally don't think are meaningful. And then I'm also filtering all the explicit words that I'm adding here, right? So this here will remove all words. You can see that it no longer starts with New Year's resolution, but also other things are maybe not. You see there's still stuff in there that might not be useful and that we could add to these stops, like FB here is probably for Facebook, or a B4, we don't even know what B4 is in this case. But you also see that reading, books, scrolling, checking, email, those are things that are maybe relevant, right? So this code here now actually creates a bar plot. I'm grouping by topic and word here. I'm summarizing the amount. I'm slicing to just get the most frequent words here. And then I'm just creating the ggplot by putting word on the x-axis and on the y-axis. I fill by topic. This just creates a nice color. And then I'm using the geom col to produce the bar plot. And I'm doing a facet plot here by topic so that we get individual bar plots per topic. This makes a lot of sense if I just run it. And you see it's quite small here at the back, but I'll produce a zoomed version. Oh, just a second, where is it? There it is, and I'm going to open it up a little bit so that we actually see something. And you see here now that there's different types of topics: career, education, family and friends, finance, health and fitness, and so on. And the most frequent words, or some of the most frequent words in these categories. We see, for example, that in tweets about New Year's resolutions that focus on career, we see terms like job, time, start, career, business, but also band or publish, right? In education, we see learn, play, school, graduate, language, guitar. We also see something, for example, in personal growth, like love, change, these type of things. We see how already the frequency of words itself tell us something about the actual topic. It matches to a certain degree, but only to a certain degree, right? So we see also that happy is something that occurs in several different ones, right? Also perhaps interesting, the health and fitness category, which is about stop primarily, stop something like smoking, cigarettes, I assume. It's also about gym, which is probably not stopping, but starting gym, right? So yeah, we can see that this visualization gives us an idea what we are talking about. And this was also already the first exercise to talk a little bit do we see, do the works make sense? I believe they do. So now we're going to start engaging with word embeddings. So as mentioned in the lecture on Monday, using word embeddings instead of the document feature matrix is a more powerful way, and maybe a more informative way to represent words, because we present it in a multi-dimensional vector space, right? I showed this figure here. Again, word embeddings is this idea that we can rank or quantify words on various dimensions, sometimes up to 300 or 700 different dimensions, right? Again, what this means is that in a multi-dimensional vector space, certain terms are closer to one another, and sometimes also the distance between two ones tells us something about their meaning, right? Again, let's get back to this classic example. The distance between man and women may be very similar to the distance between king and queen. And similarly, on a different dimension, the distance between king and man may be similar to the distance between women and queen. And this allows for mathematical operations, right? So for example, if we subtract man from king and add women, then we get a vector of numbers that is very close to the vector for queen. So now we would like to get these word embeddings for our tweet corpus. there's different ways to do that. We either would have to train a shallow neural network ourselves to find the weights that correspond to these values on these dimensions, or we just take pre-trained word embeddings, for example, from the Glove word embeddings. This is actually what we will do. This is already what I've done in the lecture as well. So we have to downloading them, and let's try to understand them. Now, what's really important, this code chunk here would actually download all word embeddings for 100 dimensions of the Glove 6 billion parameter model. Don't do that. Please do not run, I'm saying it here explicitly, do not run this, because it's actually a quite large data set or quite large file. It's almost too large for you to necessarily have to be downloaded. I just included this here because this is how you get the full data set of word embeddings with 10,000s of words in all the dimensions. We can even ramp this up to 300 dimensions if we would want to, but that would be even bigger. It's several gigabytes large, so don't do that. So instead we'll use a small subset with only 50 dimensions and 10,000 words that we can simply assess through the supplementary material of the book by Wouter van Attenveld. This is how we can get it. We have to wrangle it a little bit to get it into a tidy format, so don't worry too much about the code here. Just run it and we'll see where we're heading. And let's quickly check out this data set. I'm doing this simply here by arranging by the first dimension and selecting the first 10 words. So let's have a look at this. I already showed these actually in the lecture. So these are the 10,000 words included now in this package that we downloaded. And if we decreasingly arrange it from the first dimension, we see that it has something to do with transport, maybe even a little bit with flying, right? So the first word is Airbus, spacecraft, Fiat, which is more transport, cars, obviously, than planes. But here we also have planes. Then we also have bombings. So maybe it's a bit related also or connected to terror attacks related to planes. So you'll see there's some meaning embedded in this dimension. We do not know exactly what this dimension is, but we can imagine that across 50 dimensions, the meaning of a word such as spacecraft or planes is somehow captured. Now we need to use these word embeddings to embed our tweets, right? To connect the dimensions that are connected to each of these words to the words that are actually in our tweet. In order to do that, it's actually fairly simple. We just take our tidy tweets and we inner join the word embeddings. This inner join command simply puts them together by checking which word occurs at which line in the tidy tweets and mapping the exact line of the word embedding data set that contains this particular word. Right, so if we do this, and I again run just the head, you'll see now that we have still our original tidy word or tidy tweet data set, but now all the dimensions are added depending on what word is first here, right? So the word read on the first dimension is minus 0.38 and so on. Now, a lot of these word embeddings may be doubled now in this data set. So just as long as we play around with this, I would suggest that we just use unique words so that we get down to a data set that only contains unique words and not double words. And this can be done, for example, by now selecting just word and the dimensions. So I'm removing the name and the topic. And then I'm just using the function unique, which will only retain rows that are unique, that don't have any doublings. Okay. Now that we have done this, we can investigate similarities between words from different tweets. For this, we need to transform our unique embeddings into a data matrix. It's technically not necessary, but it speeds up computation quite a bit. This is why we'll do it. And we further have to create two functions that allow us to find relevant words and its dimensions and to find similar words in the corpus. So this looks a little bit intimidating. I'm just providing you this function, so you don't really need to learn how to create functions yourself. But this first line of code takes this unique embedding matrix and creates a matrix out of it. Then we use the word as row names, and then we just do a little transformation that makes it a little bit easier to handle the computation. And if we check this out, it's a little bit of a different type of representation of our initial word embeddings. Nothing that we have to worry about too much. Now we create a function that takes the word embeddings itself and then the word that we want to investigate. That's basically just searching for the word in this word embedding matrix. Right? We call this word vector. And then we create a function that takes this word vector, or that uses this function in between to compute similar words and maybe also allow us to look at several words that are somewhat similar. Don't worry about how this is actually programmed. Let's try it out. This way we'll actually find exactly what we're looking for. Right, so now we can take this WS-similar function, provide it with a tweet matrix, and then within it, extract the vector from the tweet matrix for a particular word, and then provide the 10 most similar ones. So if we do this for smoking, we get the following. We see that the embedding for smoking is closest to the embedding for alcohol, right? Maybe not too surprising in tweets about New Year's resolutions. Also to cigarettes, drinking, cigarette, we haven't really differentiated between, we haven't really aligned plurals and negative, sex, drugs, habit. So a lot of things maybe that are seen as bad, tobacco, and so on. Now if we take something perhaps more positive like guitar, we'll see the most similar ones are other instruments like bass, drums, piano, music, singing, songs, bands, lyrics, musical. Again, making a lot of sense. If you take a very positive word like happy, for example, you'll see that it's actually a bit less clear what is the most similar here, but a lot of tweets apparently seem to suggest that happy everyone, or really me should be happy. It's close. Right? So we see that there's some meaning in these word embeddings that leads to these similarity scores. Now, the interesting part also about word embeddings, which we mentioned before, is that we can do computations, mathematical computations with them, right? So, for example, let's extract the word embedding vector for the word college. This is what I'll do here. Just to give you an idea what this is, it's really just the 50 dimensions, the 50 values on these 50 dimensions for the word college. And I'm doing the same thing for drinking. And now, in this next steps, I just take college and subtract drinking from it, right? So college, subtracting drinking. It's not maybe semantically that meaningful, but we can, for example, what happens if we are going to college without drinking, right? And I'm saving this as what this is. And then I'm again taking my function to find similar words and just provide it with this vector. With this, right? This is nothing but a similar word embedding vector. It's just not, we don't know yet what it is. So I'm looking at the most similar words to get an idea of what it could represent, right? College minus drinking. And if we look at it, I'm now looking at it a bit more, we see that, well, one of the most closest one is graduate, university, fellowship, then a certain ranking, which is a bit less, also again, graduates here, Michigan, interestingly specific, Knights, graduation again, associate. So apparently what it suggests is that subtracting drinking from college apparently is similar to words like graduation. Now you can of course read a lot into this, like, okay, you shouldn't drink at college because then you're more likely to graduate. Maybe that was captured by this meaning, but you see that there's some meaningful aspect is being retained by these mathematical computations. Now here's a little exercise. What if we can find something else, right? Can we find something that, or is another mathematical operation that makes sense, right? So this is what we exactly are going to do here. We can basically just take this bit here and just change up a little bit what we're doing here. So maybe let's not use college here, but rather what could we be interested in? Maybe, let's say books. Right, so I'm taking the vector for book. Let's say just book should be in there, or books. Well, let's say books. And I'm adding also friends to this, right? Friends, right? So this should both lead to vectors for books and friends. Now I'm saying, okay, what if I take books plus friends? So that's the question, what is books plus friends, right? So let's see whether that makes sense. I have no idea whether that actually makes sense. So let's explore what words are similar if we combine books and friends. And we'll see that, okay, friends and books, of course, interestingly, writing and stories, a couple, life, love. Okay, so friends and books apparently are things that are to some degree similar to love, life, children, also work. Interesting, talking and learning. Let's maybe explore something else, right? So this is always interesting to see. I remember something funny like for example, let's take the Netherlands. And let's take maybe cheese, if it exists. I don't know if it exists in there, or then let's see, I'm not sure. No, it's not in there in the Netherlands. What could be New Year's tweets? Let's imagine fireworks and healthy. Maybe something like this. And let's hope that these are in there. Yes, they're both in there. Let's take fireworks minus healthy. And this leads to what? Blast, protest, stones, right? So if we take away healthy from fireworks, we get also smashed and loud and bang. A lot of different things that also actually make sense. Could also be explosion, that could burning, right? That makes sense that comes up here as well. Okay, you see that we can make now mathematical computations with words, which is a somewhat curious thing. But this is of course all just a stepping stone, because now a model can also take advantage of this embedded meaning. This is what we'll use in the text classification part of this tutorial. So our goal is now to predict the New Year's resolution category from the tweet. And this is actually a fairly difficult task because the tweets are often short, they're cryptic, right? And we're going to do this now, or try to improve this now, by using these word embeddings. Remember, the pipeline for this looks as follows, right? We have our text, it is labeled, we want to train it, but we'll first add word embeddings to get an embeddings matrix. We split it into training and test data, then we build a classifier based on these word embeddings, we validate, and then we'll use it to potentially classify new tweets, which we won't do in this tutorial, but this is the general idea. As always, we need to prepare the dataset a little bit. And I actually want to make the task a little bit easier because there's a lot of different categories in this dataset. And usually the supervised machine learning classic algorithms have some trouble predicting more than 1, 2, 3 different categories. So we'll keep it simple and just ask to algorithm to find ways to classify tweets in either the category personal growth or other, right? So we're kind of interested in whether they can find personal growth related tweets about New Year's resolutions, and then the rest will just be thrown into other. So we have to first create a label that we want to predict that is just personal growth or other. This is what's happening here. So I'm using an if cell statement here automatically. And then we'll split it. It's a fairly large data set, so we split it 95% versus 5%, so I only retain 5% for testing. Okay, here I'm seeing actually that we haven't loaded our library tidy models yet, which we need to do. And now it's actually working. We have our training and test data. And now we have to create a recipe, very similar to what we've done in the last tutorial, for the pre-processing, but here we not engage in much pre-processing except that we tokenize and add the word embeddings. There's just one thing that I'm actually doing here as well. I'm again getting rid of some of my explicitly defined stop words, like the tweet itself and stuff like that, because they will not be meaningful. I'm not sure whether this will actually improve the performance, but in my mind it actually does make sense. So first, recipe, we want to predict the label, which is just personal growth versus other, by text. We want to tokenize, we want to remove stop words, and this is just the ones that I already predefined. And then this is the really important one. We're going to add the word embeddings that are stored here in the word embeddings matrix. And because they are going to be applied to sentences, we also have to specify the method and how they are going to be aggregated to the sentence. And that in this case will just be the mean, or the mean of the different word embeddings. Okay, this is going to be our text recipe. Then, because we want to fit a neural network model, which we already did in the last tutorial, we define our MLP, our multi-layer perceptron. Again, this is done by using the function MLP from the Brûlé package. This is important. And thereby we have to specify the architecture. So we do this by using 600 epochs. We use, again, just 6 neurons in our hidden layer. We don't make it very complicated. We use a penalty of 0.01 and a learning rate of 0.02. So you see these are pretty much the exact same architecture that we already used in the past tutorial. We keep it at that. Again, we'll set the engine to Brûlé because that's where the MLP function comes from, and we set the mode to classification because that's what we're after. Then we create the workflow. My text reg was not found because, I did not load another package that we need, and I'm going to add it just here, which is text recipes that we also need in order to set this up. So now that I've done this, it should work. We can create the workflow, and now I'm fitting the workflow to the training data. This will take a moment, so let's see how long it takes. And again, in my case, it already is done, but I wanted to mention that in case your computer cannot do it, please do not be frustrated. It's not your fault. It's just a lack of power in order to do this. If that is the case, one way we could work is to decrease the training data, just use half of the sample, not 95% of the sample, then it may work better. You could also decrease the number of features by using just, I don't know, the 500 most frequent words and so on. There's ways to reduce the data in order to make your computer fit this. So, think back about the last tutorial. How can we assess the performance of this neural network? If you remember, the next step would be predicting our test data, right? Predict is the function that we can use here. We provide it with our fit, our classifier, and then we have to specify new data, which in this case is the train data, the test data. If I run this, you see how it predicts it. The first tweet was predicted as other, the rest as personal growth. And in order to make this meaningful, we bind columns in this case from the test data so that we also see the actual label. Right, so again, I'll do this. Now you see that I'm putting all of it together, and somewhere in here is also the label at the end here. Perhaps it's meaningful to select them so we only keep what we want to have. So on the one hand, predicted is the pred class. That's the actual prediction here, the first column at the bottom. And we keep also the actual, which is the label. Right, if I do this, here you see this is how it was in the data set labeled. This is what the algorithm came up with. We already see here that it does here some right, here's one error, but otherwise it looks actually fairly good. Let's see how well it did. I'm always putting this into a object because I feel like it's helpful to do it this way. Now we have to define what metrics we want to get. So metrics set, again, this is going to be accuracy, precision, recall, and the F measure. And then we can use this class metrics on this here, and we need to provide the truth, which is in our case the actual, and the estimate, which in our case is predicted. These are the two columns that we want to compare. And if we run this, we get our estimates, and we'll see that our neural network here, based on word embeddings as inputs, actually is not too bad at classifying these tweets, which are fairly cryptic and short, right? It's a fairly difficult task, into the category personal growth or rest, right? The accuracy means that in almost 73% of the cases it does it right. And we also see that recall actually is even a bit higher here, and overall F measure is quite high therefore. So not even that bad. Now, the next exercise and the last exercise for this tutorial is, again, well, we chose our network architecture somewhat randomly, and we could now go ahead and try to find a new one. I want to spare you the trouble of going through a grid search again, although this would be probably a very good idea to now go ahead and set this up as tuning framework in which you can explore different combinations, because this may take a while. What we'll do for now is just take this bit here put it down here, and we'll just change up randomly, just by intuition, what could maybe be better. And for now, I'm actually going to do something slightly more complex. I'm going to add a second hidden layer, and I'm doing this by, for example, saying the first should be 32 and the second 12. It's a fairly arbitrary choice, but I'm hoping that this increased complexity within the hidden layers may help in doing this. I'm also lowering the learning rate a little bit, and hopefully thereby, maybe here to 0.01, also increase the possibility. And I also, I'm not changing the epochs here. So this is my new specification. I'm keeping this. Now the workflow and the fitting needs to be updated, so I'm taking this bit as well. And I have to, of course, make sure that I'm using the right specification. I did not change the text recipe here because I don't think that that's influential. So now I'm having new workflow, and now the new workflow needs to lead to a new fit. So let's run it. This will take maybe potentially a bit longer because it's a more complex model. It has more hidden layers. It has a lower learning rate, so it takes longer to adjust the things. But again, my computer is already done. So now I'm taking, again, the prediction and the testing. And I have no idea whether this will actually lead to a better one, but I'm hoping. I'm hoping that it leads to a better performance than the previous one. So right, again, this is the second prediction, so I'm keeping this at second, predicted, and now let's check. And I actually don't think that I'm that much better here. It looks very similar. I'm actually probably a little lower. I think it was at 0.73 before. Let's check again in comparison. I I increased the decision by one digit on the, or by 1 point on the third digit, but I decreased almost all of the others, so not really. Again, it's always nice to maybe visualize this and to show you how that works. We combine rows here using the predict, always this bit here. And then from the first, and to make them distinguishable, we add the actual algorithm that was used. This is a very similar visualization now that we already had last time in the last tutorial, which is now in this case neural network simple, I call it, and then I'll copy paste this, add this to here, and call this more complex. And this just binds it both together, as you can see. This is what the table looks like, and this we can of course feed into a ggplot, where on the x-axis we put the metric, on the y-axis we put the estimate, and we fill by algorithm or color. I don't remember exactly. I'm actually going to run this to check how it looks like. It's not probably in the right format yet, so we actually need to adapt this a little bit. You see that they're stacked on one another, which is not great, so I'm adding here position dodge with a certain width. I'm just playing around here with 0.5, maybe that's enough. Let's check. No, not yet. Now they're still overlapping, but they're next to one another, so maybe 0.5 is the right one. Let's again check. Okay, still not enough, so maybe I need 1. All right, now they're next to one another, right? Next to one another, that's nice. Exactly what we want. What I don't like is that it's on the wrong axis, so I'm using a chord flip. Actually, let me pull this up so that we can immediately see what we're doing here, right? So now it's very close to what we already had. Still a couple of things that I don't like, so I'm adding a theme, minimal, nicer, and I'm also gonna define the labs. This is the performance, axis, actually not the performance axis, nothing. Y is performance score. And yeah, that's pretty much it. Let's see. Yeah, that looks pretty good. Remember, we also added here the numbers. If you would like to do that, that is a geom text. And the geotext requires a different aesthetics. It says the label, which in this case is also just the estimate. If you do this now, you'll see that it adds these numbers, but it doesn't look great. So we need to round them. Okay, this looks better, but it also needs to be dodged. Similarly, position, dodge equals 1. Hopefully that will do the same thing. And yeah, and now we have those. We can further play around with this. The one thing that I always like to do when I look at performance is to put the y-axis on a certain limits, which is 0 to 1. That's the limit that the scale has. And that way it just all looks a little bit better. All right, so here we have it. The comparison, you'll see that they're almost the same. The simple neural network is actually slightly better in recall and accuracy. So we didn't really actually improve the model performance based on just adding more hidden neural layers. That was all for this tutorial. I hope you have learned a little bit about how to add the word embeddings. You see, it's not that different from just a standard supervised machine learning pipeline. The biggest difference is just adding this step here to the recipe. That's actually the most important part. And otherwise, it just almost stays the same. In this case, it seems to work quite well. We get high performance scores. And actually, in a lot of cases, adding word embeddings instead of just using the document term feature matrix or document term matrix is meaningful, increases the performance, and therefore is a very good step to do. With that, I hope you have the tools and or have learned something about how to use this. Work through this tutorial yourself. Check out the solutions later. And if you have any questions, please do address them to your teachers. Thank you.